Take a look at a porcelain cup resting on a table. We instinctively understand that the cup exists independently of us. It has clear boundaries, a specific location, and if you move it across the table, it travels through space over time. In physics, this assumption is known as local realism. It is the idea that objects exist objectively and only interact through direct physical contact or signals traveling at or below the speed of light. This framework matches how the human brain evolved to navigate the world for survival. But at the subatomic scale, this physical framework stops working. When we observe particles like electrons and photons, they refuse to behave like solid objects or occupy a single definite position. This animation illustrates a condition called superposition. Before being observed or measured by an instrument, a particle doesn't actually have a fixed state. Instead, it exists simultaneously as a hazy range of unresolved possibilities. This is different from flipping a coin and covering it with your hand, where the result is already decided even if you haven't seen it yet. In the quantum realm, the state of the particle is literally undecided until the moment of interaction, which forces it to snap out of its probability cloud and adopt a definite property. If the universe operates on a bedrock of unresolved potentials rather than solid objects, it means our biological perception is structurally blind to the true nature of reality. The most extreme break from our everyday logic happens when two of these undefined quantum particles interact with each other. Under the right conditions, they merge. Instead of having two separate identities, they become part of a single shared mathematical system known as a joint wave function. This is quantum entanglement. Once entangled, measuring the state of one particle instantly determines the state of the other. This happens with zero delay, even if the particles are separated by millions of miles of empty space. Albert Einstein rejected this concept, famously dismissing the phenomenon as spooky action at a distance. To him, any influence appearing to travel faster than the speed of light threatened the very rules of relativity. To reconcile entanglement with the laws of locality, Einstein proposed a workaround called hidden variables. He argued that the particles aren't actually communicating across space. Instead, they must carry tiny, unseen internal instructions, programmed from the moment they were created to dictate their outcomes. Albert Einstein and his colleague Niels Bohr spent years debating this point. They were arguing over whether the universe possesses an objective reality when no one is looking, or if reality is actively constructed by the act of observation. Hidden variables offered a logical escape route. It was a way to keep the universe localized, structured, and compatible with our inherited intuition. For decades, the debate remained philosophical. Then, in 1964, John Bell found a mathematical way to put Einstein's intuition to the test. He proved that if hidden variables did exist, there would be a strict statistical limit to how often entangled particles could correlate their behaviors. By the 1970s, researchers had developed the precision instruments required to physically test Bell's theorem. They generated entangled photons, fired them in opposite directions, and painstakingly measured their states in a lab environment. The results were definitive. Bell's mathematical limit was consistently exceeded. The particles were synchronized far beyond what any pre-written internal code could allow, proving that local hidden variables do not exist. This evidence introduces the concept of non-locality. The physical space between the particles does not dictate their relationship. They do not send signals to one another because, at a fundamental level, they are not two separate things. In classical physics, objects exist first, and relationships form between them later. Entanglement shows that the relationship comes first. The unified system exists as a whole, and the individual parts we see are merely distinct expressions of that underlying system. The empirical data confirms that the human concept of a disconnected, strictly localized universe is an approximation that fails at the most fundamental level. If separation is an illusion and reality is a non-local web of instant connections, why does a porcelain cup on a table feel so distinct and solid? The bridge between quantum behavior and our predictable world is a process called decoherence. Entanglement isn't rare. It is happening everywhere, as every quantum system constantly interacts with the air molecules and thermal radiation in its environment. Look at this diagram. A pristine quantum state, the sharp wave, is bombarded by environmental noise. Its delicate information dilutes, scattering across millions of particles until impossible to track. As connections spread, quantum correlations wash out, averaging into the stable behavior we observe daily. The predictable world we interact with is an emergent layer. It is a simplified byproduct of entanglement spreading beyond our ability to observe it. We struggle with quantum mechanics because the human brain is evolved to analyze the world by breaking it into isolated pieces. Entanglement reveals relationships that cannot be reduced or simplified without losing the truth of the system. Our difficulty in grasping these mechanics reveals that our intuition is a specialized tool, optimized for everyday survival, but insufficient for the subatomic. The classical world is a stable, consistent surface, but entanglement shows that beneath it, the universe is defined by interconnected relationships, not independent parts.